Hello students, welcome to Educate. Today we are going to start from Solenoid onwards, chapter 4 of class 12 physics. So let's start from here. The solenoid. I think you have basic idea about solenoid that you have studied in 10th standard. So now we are going to find out the magnetic field produced by a solenoid. So here the diagram is shown, the direction of magnetic field and its intensity is shown here. So inside the solenoid, you will see that field is almost uniform and outside it becomes almost zero. If you read it, you will find that here the magnetic field due to a section of solenoid which has been stretched out for clarity. Here these are the turns. Here wire is entering, here wire is entering. This is like this. So this portion is shown here, like when we draw solenoid like this, so it is cut like this from between. So this point, entering points are shown here, this point, these points, corresponding points are shown. Similarly, this is coming out. Suppose current flows like this, so this is direction, right? So that thing is shown here. Now, so the magnetic field due to section of solenoid which has been stretched out for clarity, only the exterior semicircular part is shown. As you know, when you draw like this, so here this portion is shown and this portion, this portion means lower portion is removed. Only this portion like this, like this, like this. So suppose current is flowing like this. So here current is entering, here current is coming out. So these portions are shown here by this diagram. And I particular, if you remember, if there is a wire, it carries current, then field lines will be like this. They will be concentric circles. The same thing is shown here, right? So one more thing you will notice here, if you enlarge it, you will see that direction of field line is like this here, but due to this field line is like this. So what is happening? The effect is being cancelled. This is going in this direction, this is going in this direction, so net effect inside will get cancelled. So that thing you have to understand. Here in second figure, what you notice, in this case just one turn is shown here, that current is entering like this. So here magnetic field line will be like this, here magnetic field line will be like this. So you understand, we have already studied that if we draw this symbol like this dot, what does this mean? This means field is coming towards us, means if we take this page, the field will come out, and if we put cross inside, it means field is entering. So here there is cross, it means field is entering, and here entering means it is inside the page, and this is here dots are given, it means field is upward or field is outside, you can say. So this is basic point that you have understood. The magnetic field of finite solenoid is shown here. Now, if you read it, figure this one displays the magnetic field lines for a finite solenoid. We show a section of this solenoid in an enlarged manner, right? Then it is clear from the figure that the circular loops that the field between two neighboring turns vanishes. As I told you that if you consider, suppose this portion, so here field line direction is like this, here field line is, but here if you observe in close vicinity, so direction of this is like this and direction of this is like this, so they are getting cancelled. So that thing is explained here. Now in order to find a magnetic field, we draw this type of diagram. Here there is cross, it means current comes out, means magnetic field will be perpendicular downward. Here there is dot, it means field is perpendicular upward, right? So we consider a current loop, or we consider a loop here, just if it is visible. So A, B, C, D, E. So we will check what is contribution of part AB, then BC, then CD, and then AD or DA. So here outside the solenoid, field will be 0. And here this is perpendicular to the direction of magnetic field here. So what will happen? Here contribution due to this will be 0, contribution due to this will be 0, only contribution due to this will be considered. So we are going to see it in detail. The magnetic field of a very long solenoid, we consider a rectangular Amperian loop ABCD to determine the field. So this is Amperian loop because we are going to make use of Ampere circuital law. And you know what it is. So here, so solenoid is made longer, it appears like a long cylinder metal sheet. Previous figure represents this idealized picture. The field outside the solenoid approaches 0. We shall assume that the field outside is 0. The field inside becomes everywhere parallel to the axis, as is clear from the picture. And then we consider a rectangular Amperian loop ABCD. Along the CD, field is 0, as argued above. Along traverse section BC and AD, the field component is 0. Means like this, if we consider this, this, this and this. Here, field will be 0 for this. This is outside the solenoid. This part, if you observe the previous picture, here perpendicular, so it will cancel out, and this is also perpendicular, it will cancel out. Only this will contribute. And now here we have to find out how many turns are there. If there will be n turns per unit length, and suppose this length is h, then total turns will be h into n. So that thing we are going to consider. So thus, these two sections make no contribution, means perpendicular section no contribution. This here field is not there, so you can ignore it. Only this portion will be left. So that thing is written here. The field component is 0. Thus, these two sections make no contribution. Let the field along AB be B. AB means this portion is B. Thus, the relevant length of the Amperian loop is just L. As I told you, this is to be taken as H. Now, let N be the number of turns per unit length. Obviously, if length is H, then you have to multiply it to N. So, total number of turns you will get, and then you have to find out the current, because Ampere's circuital law is used when the loop is enclosing certain current. So here current enclosed will be IE, and then if I is current in one single turn and there are NH turns, then total current will be I times NH. You have understood? I think so. You have got total I. So IE, let's write it, and then I is current in one turns and total turns are N into H. So this will be the current, right? And then what is Ampere's circuital law? Integration B dot dl equal to integration closed integral B dot dl is equal to mu naught times I, right? So here dl means, here you can keep B outside, theta will be 0 degrees, so cos theta will be 1. So B integration dl and equal to mu naught times I. I is INH, right? So what you have got here, integration dl means total length. So this will give L or H we can take. So B into H will be mu naught then N, I and H. So H will cancel out and we will be left with B equal to mu naught N I. So this is expression for magnetic field due to solenoid. So I think you have understood. Here N is number of turns per unit length. Now, there is one question based on this concept. Question is simple. Question says a solenoid of length 0.5 meter, right, has a radius of 1 cm and is made of 500 turns. It carries a current of 5 ampere. What is the magnitude of magnetic field inside the solenoid? So you know very well that magnetic field inside the solenoid is B equal to mu naught N I. So what all you need? You need current, and N means number of turns per unit length. So total length divided by, total number of turns divided by length. So length is 0.5 meter and number of turns is 500. So 500 divided by 0.5 will give 1000. So we have got N equal to 500 divided by 0.5, that is 1000 turns per meter. So we have got N, mu naught is already known, current is given 5 ampere. So let's put the values. So B equal to mu naught Ni, mu naught is 4 pi into 10 power minus 7. Number of turns we have got 1000 and then I is 5 ampere. So after evaluation you will get 6.28 into 10 power minus 3 Tesla. So I think it's clear. Now let's see next thing, force between two parallel conductors, two parallel currents. So if you remember, if there are like charges Q, say it is positive, this is also positive, say Q1, Q2, then what will happen? They will repel each other, right? This will move in this direction, this will move in this direction. If they are unlike, suppose this is minus Q, this is plus Q, then what will happen? They will attract each other. But in case of current conductors, the case is just different. If there is one conductor that is carrying current I1 in this direction, another is conductor is containing current, say this is I1, say I2, then they will attract each other, right? These conductors will attract each other. If current is reversed in one conductor, suppose one has current in this sense, another has current in this sense, then they will start repelling each other. So this is practically found, right? So here we are going to find out what is the force between these two conductors, right? Whether it is repulsive or attractive. So here, if you wish to read, so let's read together. First, let's see what is written here. Here there is one conductor carrying current. This is another conductor carrying current. This current is IA. This current is IB. Separation between the two is D. Since current is in same sense here, direction shows, then they will attract each other, right? So we are going to derive the relation of force per unit length and also direct force we will find out. So here two long straight parallel conductors carrying steady current IA and IB and separated by distance D. BA is the magnetic field set up by conductor A at conductor B. So here what is happening? So let's see an insight and after that we will read whatever is given there. So suppose this is conductor and it carries current I. So at this point, suppose, so it will give rise to magnetic field, right? And then in that magnetic field, if there is another conductor, say it carries current I1, so this will experience a force, right? And if you remember, F equal to BIL sine theta, here theta will be taken to be 90 degree. So this is force. The same force we are going to calculate. Because of this conductor, there will be magnetic field. So this term will come from this conductor at the side of this conductor, and then I will be current, this current, and L we will consider certain length of this, and generally we find force per unit length. So this term will vanish. So that we are going to do. So let's read it and then we will try to understand. If there is some difficulty, we will try to resolve it. So as I told you, everything you have understood. So now we are going to see the situation. So here, if first conductor is carrying current, in that case it will give rise to magnetic field given by BA equal to mu naught IA. I'm making it little bigger so that it may become clearly visible. So here, if one conductor is carrying current, so due to that magnetic field will be mu naught I A divided by 2 pi D, where D is the separation, right? And this is at the site of second conductor. Now, second conductor will experience a force, and that force will be given by formula BIL, right? Theta will be taken as 90 degree. So, FBA will be this BA times second conductor, its length, times current carried by it. So, after putting values, we get mu naught IA IB divided by 2 pi D. I think you have understood. Now, we generally calculate F divided by L. So, force per unit length we will get. Now, if we reverse the case, that we find the magnetic field, suppose this is conductor, say this carries current IB and this carries current IA, right? And separation, as we have discussed, that it is D. So, now we are going to consider reverse case. We will consider that this is carrying current IB and it is giving magnetic field at the site of second wire. That will be equal to how much? This time we will write BB equal to mu naught IB divided by 2 pi D, right? And then we will find out force F, we will write AB, right? So same thing will be there. This time in place of FAB if we write, so it will be IA times L into BB. So we will get same result, alright. That is why we say here FAB equal to minus, because Newton's third law is applied here also. It's obvious. If conductor, this is exerting force in this direction, this will exert force in this direction. So there will be attractive force provided the current is in same direction, right? So that is why FBA equal to minus FAB. Here, note that this is consistent with Newton's third law. Thus, at least for parallel conductors and steady currents, we have shown that the Biot-Savart law and the Lorentz force yields result in accordance with the Newton's third law, right? Then here same thing is written, force per unit length they have divided by certain length. So in certain questions you will find either you have to find out force per unit length, or you will be given the length of one conductor that will be finite, then easily you can evaluate, right? So here there is one important note. It turns out that when we have time dependent current and or charges in motion, Newton's third law may not hold for forces between charges and or conductors, right? An essential consequence of the Newton's third law is in mechanics is conservation of momentum of an isolated system. This, however, holds even for the case of time dependent situations with electromagnetic fields, provided the momentum carried by the field is also taken into account. So we will see these things later on. So up to here thing is clear, right? Now, so we have got the expression for force F per unit length if we write, otherwise we generate mu naught upon 4 pi. What was the formula? I1, I2. This was not 4 pi, the mu naught of I1, I2. Here you can write length if you wish, and then this is 2 pi and R. Here in our case it was 2 pi D, correct? And if you find F upon L, it will be mu naught I1, I2 divided by 2 pi R. So here we can do one thing. Suppose we take a length equal to 1 meter, right? I1 equal to I2 equal to 1 ampere and R is 1 meter. Then what do we get? F upon 1 mu naught 1 into 1 divided by 2 pi. So we will get mu naught upon 2 pi, force between two conductors, right? When placed at a separation of 1 meter, then force between them will be equal to mu naught upon 2 pi Newton. So this is used to define 1 ampere current. Here what we have assumed that currents are in conductors is 1 ampere in each, right? So the ampere is the value of that steady current. This is very important thing. You have to memorize it or you have to understand it. The ampere is the value of that steady current which when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum would produce on each of these conductors a force of 2 into 10 power minus 7 Newton per meter of length. Did you understand? Is there doubt? Here what we have done, here we know that F equal to mu naught I1 I2 into L divided by 2 pi r, right? So first we write force per unit length, then mu naught I1 I2 divided by 2 pi r. Then we make assumptions because our purpose to define 1 ampere. So if we put here I1 equal to I2 equal to 1 ampere, right? R equal to 1 meter. This per unit length, keep it intact. Don't write it as 1. Force per unit length. So will be equal to mu naught upon 2 pi. And if you remember, mu naught upon 4 pi equal to 10 to the power minus 7. So mu naught upon 2 pi will be equal to how much? Mu naught upon 2 pi will be equal to 2 into 10 power minus 7. Correct? So here it will give force per unit length will be equal to 2 into 10 power minus 7 Newton per meter. So here one very important conclusion you can draw that if there are two conductors whose separation is 1 meter and they carry current 1 ampere, then force between them will be 2 into 10 power minus 7 meter. So we can say if there are two conductors and force between them is 2 into 10 power minus 7 Newton per meter and they contain equal current, in that case we can say that their currents are 1 ampere each. So this definition is used to define ampere and you have understood. This definition of the ampere was adopted in 1946. It is a theoretical definition. In practice, one must eliminate these effects of the Earth's magnetic field and substitute very long wires by multi-turn coils of appropriate geometries. An instrument called the current balance. You will study about it. So an instrument called the current balance is used to measure this mechanical force. The SI unit of charge, namely the coulomb, can now be defined in terms of the ampere. So when a steady current of 1 ampere is set up in a conductor, the quantity of charge that flows through its cross section in 1 second is 1 coulomb. Correct? Now, we are going to see one example. Example says the horizontal component of Earth's magnetic field at a certain place is 3 into 10 to the power minus 5 Tesla. And direction of the field is from the geographic south to the geographic north. A very long straight conductor is carrying a steady current of 1 ampere. What is the force per unit length on it when it is placed on a horizontal table? And the direction of the current is east to west and south to north. Did you understand? So magnetic field, as you know, that if a conductor is placed in magnetic field, then it will experience a force, and that force is given by BIL sine theta. If theta is perpendicular, then force will be maximum. If theta is parallel or if theta is say 0 degree or 180 degree. That is, wire is parallel or anti-parallel to the field. In that case, force will be 0. So here two situations are shown. One is for parallel, another is for perpendicular. First case is for perpendicular, so theta will be 90 degree. So we can easily evaluate force per unit length. Here F equal to BIL sine theta, and this gives F upon L, that will be BI, right? We can put the value. So I is given in our question, that is 1 ampere, and value of B is given 3 into 10 power minus 5 Tesla. So after putting those values, we get 3 into 10 power minus 5 Newton per meter, right? This is larger than the value 2 into 10 power minus Newton per meter quoted in the definition of 1 ampere. Hence, it is important to eliminate the effect of the Earth's magnetic field and others stray fields while standardizing the ampere, right? Because this will also affect the value. The direction of the force is downward. This direction may be obtained by directional property of cross product of vectors, that you know. So I'm not going to tell you what is cross product. Suppose you consider the direction. So if you remember, so suppose here we are considering two quantities. One is say L cross B, if we take, and if direction of L is given, direction of B is given. Suppose length is along I cap, and this magnetic field is say along J cap. So what will you get? I cross J. So this rule, if you remember, I, J, K. So cross product of the two, if you move in order, then it will be the third vector. So here K cap. So like this. So that thing we are going to make use. Now second case, as I told you, if theta will be 0 degree, in that case there won't be any force. You have understood the basic concept. Now we are going to analyze next thing, torque on current loop and magnetic dipole. So what is that? Torque, you understand? Force into perpendicular distance. So here situation is shown. Let's analyze it first so that thing may become very clear. These are magnetic poles, and this is a coil which is free to rotate. Here this is external circuit. Now what happens? Here current is flowing in this direction, so there will be a force that will cause it to rotate. So force on this arm CD will be upward, this will be downward. So this is why this will rotate like this, right? And here what happens? We take this side and perpendicular distance from here, and we can find the torque. So the same thing is explained here. If you read, you will find we first consider the simple case when the rectangular loop is placed such that the uniform magnetic field V is the plane of the loop, right? This is illustrated in figure 4. This one we are talking about. The field exerts no force on the two arms AD and BC. AD, this and this, right? AD and BC of the loop. It is perpendicular to the arm AB of the loop and exerts a force F1, right? Here it is perpendicular to the arm AB. Where is arm AB? Arm AB is this, correct? So this arm, we are considering this arm. So on these arms there will be force, right? So it is perpendicular to arm AB of the loop and exerts a force F1 on it, which is directed into the plane of the loop. That is shown there. So we can write force equal to BIL sine theta. Perpendicular means theta will be 90 degree. So BIL. So what is length? What is current? So current is I, magnetic field is B, and length is here. Separation is B. So side length is given. That will be cleared like here. It's B, right? And this is A. So we are taking force into perpendicular distance. Force is like this and perpendicular distance is like this. Between distance between the two arms we are taking. So F1 equal to BIL. Similarly, it exerts force F2 on this arm CD. That will be also same. So what is happening? It is forming a couple. Although net force on the loop is 0. So, but net torque will not be 0. So for considering torque, we have to take force and the distance from the axis. So that will be just A by 2. So here we write torque equal to F1 force times A by 2. Similarly, force times A by distance will be same. This is halfway. So this will be A by 2. This is A by 2. So, but F equal to we have found IBB. So in each case we get same result. So what happens? A by 2, A by 2. We take common. That will become A. So we will get IABB. And if you observe carefully, area of the rectangular loop is AB, right? Length and breadth. So here we can write it like IAB into B, right? So in place of AB we write capital A, that is area of the loop. So we have got the expression for torque, right? But if there is certain angle theta also, in that case here sin theta will be involved. The same thing is illustrated here, but they are not. If the in second case, if there is certain angle, you can see on next page. So if there is certain angle, in this case sin theta will also be involved. In that case perpendicular distance will not be A by 2, right? It will be reduced, and when theta will be 0 degree, then perpendicular distance will become 0, and hence no torque will act. So same thing here, torque will be F1 times A by 2 sin theta. This time perpendicular distance will become A by 2 sin theta. The same is true for second one. So we will get IAB sin theta, right? When theta is 90 degree, we will get same result. But when theta is 0 degree, so we will get 0. Correct? So now we are going to define another term which is important here, that if there is a current loop and say its radius is R and it carries current in this sense, right? Then what is magnetic moment of this loop? So magnetic moment depends on its area and current, and that is written as I into A, and it is a vector quantity, and its a direction will be like this. If curvature of the fingers telling the direction of current, then thumb will point out the direction of the magnetic moment, right? So we can write in previous case what we have got, tau equal to how much? Tau was I A B, right? But I A equal to, we have assumed that this is M, magnetic moment. So we can say MB in magnitude. In vector form, we can write torque equal to M vector M cross vector B, right? And if there will be n turns, then turns will also be taken into consideration. That's same thing. Now, if you remember in case of electrostatics, what was the situation? If there is electric field like this, if you remember, and there is one dipole here, so force QE act in this direction, minus QE act in this direction. If this angle is theta, then torque equal to, if you remember, in magnitude it was just tau equal to P, which is similar to this, tau equal to MB. It means M corresponds to P, B corresponds to E. This is magnetic field, this is electric field, correct? So up to here there is no problem, and as I told you, if there are n turns, in that case the formula will become magnetic moment M will become NIA. They are talking about loop like this. There are many turns, and means one over other. Radius is not going to be increased every time. So in that case, it will become M equal to NIA. Now let's analyze one question here. First, we have to read the question and then we will analyze. So here we have to determine the magnetic field. A 100 turn closely wound circular coil of radius 10 centimeter carries a current of 3.2 ampere. Here number of turns are given, radius of the coil is given, and the current is given. What is the field at the center of the coil? What is the magnetic moment of this coil? So we are going to find out, and after that there are some more information. The coil is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The coil rotates an angle of 90 degree under the influence of the magnetic field. What are the magnitudes of the torque on the coil in the initial and final position? That is to be found. And then what is the angular speed acquired by the coil when it has rotated to 90 degree? The moment of inertia is given. So this is very good point. So let's analyze it one by one. Now, so magnetic field at the center will be given by mu naught Ni. In our question, N is given 100, I is given 3.2 ampere, radius of the loop is given 0.1. So we can find B after putting values. If you remember, mu naught upon 4 pi equal to 10 power minus 7. So here we have mu naught, that is 4 pi into 10 power minus 7. Then number of turns we can write, and then current, and then divide by 2R. So after putting values, what do we get? 4 into 10 power minus 5 into 10 divided by 2 into 10 power minus 1, and value of pi into 3.2 is given as 10. So that you can understand, because just we are putting the values. The way you like, you can put, because you will see that 100 is missing, etc., etc. So don't worry. When you put, the same thing will appear finally. So it will be 2 into 10 power minus 3 Tesla. The direction is given by right hand thumb rule. That is obvious. Now next point, we are going to find out magnetic moment. And if you remember, magnetic moment of single loop is given by M equal to Ia. If there are n turns, then magnetic moment will become n times Ia. So you can put the values. Nia, n is n, I, and then A will be area of loop, pi r square. So like pi r square, number of turns are 100, I is given 3.2, and then pi is 3.14, and radius is given 0.1. So square of it will give 10 power minus 2. After simplification, you will get 10 ampere meter square. Up to here, there is no doubt. Then comes torque. Torque is M into B. M we have evaluated. Here two positions are given. Once theta is 0 degree, when theta will be 0 degree, then this torque will become 0, and once it is 90 degree, so it will have maximum value. So after putting those values, we will get torque equal to this much, right? Now, third point, that is very important. Here you will feel little complicated. So here what is happening? Tau equal to I alpha. Is it similar to F equal to MA, right? And if you remember, A equal to dV upon dt, alpha equal to d omega by dt, right? The same thing is given here. This is value of torque. The two cases, as you know, one is I alpha, another is MB sine theta, right? And alpha is written as I d omega by dt equal to MB sine theta, right? Now, d omega by dt, here theta if we want to involve, so what do? We write I times d omega by d theta times d theta by dt, right? Equal to M, then B, then sine theta. Now, d theta by dt, if you remember, that is omega, and you can shift this d theta to RHS. So you will get I omega d omega equal to MB sine theta d theta, right? So you have reached up to here, I omega d omega equal to mb sine theta d theta. Now what is left? You can integrate it. Here you want to find out what is angular frequency. So start from 0, right here omega f final value. Similarly, theta they have given that it rotates from 0 to pi by 2. Now integrate, integration x dx, if you remember, it becomes x square by 2, and integration sine theta d theta gives minus cos theta. So these values we are going to put. So I am removing these portions because everything is clear. Up to here it is clear, this is clear. Here this will become omega square by 2, no problem. Cos theta, sine theta will give minus cos theta. We put the limits. When we put limit, so cos pi by 2 will give 0 and cos 0 will give minus 1, because here there will be minus sign. Cos theta, cos pi by 2 minus cos 0. So that will cancel this, that minus sign will cancel this minus sign. So you will get mb, right? So here our concern is to get omega. So omega 2 you can shift to RHS. So 2 mb divided by I. 2 mb divided by I, and it by squared, so take square root. So you will get 2 mb divided by I whole power half, and then put values, because our question values are given 2 into these things. 2 is 2, m is magnetic moment, and then b magnetic field divided by I, and the value of I is given, take square root, you will get 20 per second. Now, next concept is, this is general question, theory question. So we can see the question says, a current carrying circular loop lies on a smooth horizontal plane. Can a uniform magnetic field be set up in such a manner that the loop turns around itself, turn about the vertical axis? Then second question is, so let's see first question. So answer to first question is no, because that would require ta to be in the vertical direction, but ta equal to IA across B, and since A of the horizontal loop is in the vertical direction, so ta would be in plane of the loop for any B, right? So this is first portion, that is clear. Second portion is also not difficult. Let's read the question first. Second portion says, a current carrying circular loop is located in uniform external magnetic field. If the loop is free to turn, what is its orientation of stable equilibrium? Show that in this orientation the flux of the total field plus total field means external field plus field produced by the loop is maximum. Simple. So here you can easily read it. Orientation of the stable equilibrium is one where the vector area vector A of the loop is in the direction of external magnetic field. Alright. In this orientation, the magnetic field produced by the loop is in the same direction as external field, both normal to the plane of the loop, thus giving rise to maximum flux of the field. And then last question is, it says a loop of irregular shape carrying current is located in an external magnetic field. If the wire is flexible, why does it change to a circular shape? So it assumes circular shape with its plane normal to the field to maximize flux. Our purpose is here, purpose of changing shape is to maximize the flux, since for a given perimeter a circle includes greater area than any other shape. So in this lecture, this is all. We will continue in next lecture. Thank you for watching. Team Educate.